Okay. All right. So this is a joint work. Work with Larsen and Douglas Blue. So what is the what? Oh. Is everything okay?
It's Olaf microphone.
Olaf, your mic. Can you mute? Okay. So the motivational theorems are Wooden's theorems from 90s, I guess, or even 80s. So this is the first one. And this is what I called MM model, and then it was confusing for people. Sorry, yeah. Maybe I call the PMAX model, which is less confusing. But MM also makes sense. Okay, so assume ADR plus data is regular, plus V is of the form L of power set of R. So then we do let P be Pmax, followed by adding a coin subset to one coin subset to omega 3. So I noticed that a lot of people write it as add omega 3 1. It's the same as add 1 omega 3. Okay, so let P be this and G be generic. G is generic. Then VG satisfies MM plus C. It's important, there are a couple of remarks. One, in this model, so theta, just recall what theta is, yeah? This is the supremum of alpha that exists F. F is a surjection. So in the above model, in VG, theta is omega 3. Right? So theta of V is omega 3.
You have axial choice also.
Yeah, that's
VC.
This is what I mean. I mean CFC. But the other important remark is that if I didn't do the second part, so if I just went Pmax, then this would have, I guess you would still have MM plus, it makes sense, you would still have this. You will not have full ZFC, this should be F ZFC. Let me just make sure that's. So here you have ZFC. And here you have DC omega 2 on F2. But you will not have plus power set of omega 2 is not overloaded. This is a key point because that's the whole point of adding the coin subset at the end. Because if you don't, then you will not well order power set of omega 2. If you don't well order power set of omega 2, you want force choice. So you can ask why adding power, why well ordering power set of omega 2 adds choice. Well, think of if well, because we have MM plus C, right? So that means 2 to the omega is omega 2. That means the size of reals is omega 2, and V is of the form L of power set of reals. So if I well order reals, then V becomes L of power set of omega 2, basically, because omega 2 is reals of size omega 2. So it's just enough to well order this. Okay. This is the one we go to CH. So this is the CH model is not that well studied. No. So it's again, and this is the CH model. And or you could think of as called omega 1 R extension. So here we assume the same theory. Assume V equals L of power set of R plus ADR plus theta is regular. So let's now P be called omega 1 R. So we, for CH, right? We make reals. Oh, by the way, I should say, it may not be clear, but this theory implies DC, yeah, DC holds. So I don't have to, I don't have, if DC doesn't hold, if DC wasn't already holding, how could you even argue that you didn't add new reals, right? So it would be total disaster. But DC holds, so things make sense. And here we are adding, we are doing add 1 omega 2, and G is generic. Is generic. And VG satisfies CH now, plus of course EFC, plus there is an omega 1 tense ideal. On omega 1. This was, I don't know if this was before, wouldn't also force the omega 1 tense ideal omega 1 from a huge cardinal, but I don't know which one came first. Okay, so you have these two ways of going from determinacy. And of course you could ask, can you force MM in general, right? So I guess this was already asked by Woody. The question is, well, definition first. We know what star class is. But, we know what star is, but star class, this is the statement that so for every A, maybe even ask a weaker version. Yeah, let's ask him a weaker version. So UB is the set of all UB sets. And theta UB, this is the set of all, the supremum of all alpha. There exists a function from reals onto alphas. F is a surjection. And the relation x is less than or equal to y if and only if f of x is less than f of y, right? And this is UB. So it's the supremum of all ordinals for we, such that there is a surjection onto them of reals, but they correspond, when you pull it back onto reals, the trivial ordering you get on the reals, that is universally there. Right? So the question, the weak version of this is the weak version of star plus. is the theory now this is the star plus is saying basically every set of, remember, star is saying that every subset of omega-1 is in a Pmax extension. Star plus is saying that every subset of omega-2 is in a Pmax extension. Star plus plus is saying that every subset of omega-2 is in the Pmax extension of all university pair sets. So wouldn't recently prove that star plus implies star plus plus. Okay, but the consequence of star plus is that theta UB is really omega-3. And we don't know if MM plus plus is consistent with star plus. We know that now MM plus plus implies star. But even this weaker version, we don't know if theta UB is omega-3. I will ask even a different, stronger question. We don't know. For example, can you force theta UB is omega-3 or theta from large cardinals? So the point of the question is, suppose theta UB is omega-3. Does this mean that we are a forcing extension of a model of determinants, right? The same you can ask about omega-2. I don't know how to force theta UB is omega-2. Can you force? So, I mean, Wooden's question is way beyond, right? Not only we have to get MM plus theta is omega-3, we don't even know how to make theta omega-3 from large cardinals. So if you try to solve this problem, I mean, it seems like from conventional methods from large cardinals, it seems like a horrendously difficult problem. Okay, so I guess the motivational questions. Motivational question is can you force an MM plus plus be forced over determinacy models? Of models of determinacy. B is can existence of dense ideals on every cardinal, right? And the existence of dense ideals on every cardinal, every regular be forced over determinants. And okay, so A is what I will concentrate today. And I guess the consequence of the things that I would like to talk about is so there is this corollary, which of the things that I will state later on. The theory mm c plus for every kappa greater than omega 1. I guess I'll equal to. Now square kappa. You can also put the round bracket, but it's always confusing. Basically, you want to put the round bracket for regular cardinals, I think, plus for all kappa greater than omega 1, kappa regular implies not square, round bracket kappa is weaker than wooden cardinal. That is limit of wooden cardinals. This has some consequences for inner model theory because we thought that this is a strong, at least a strong, a super strong. And so there were a lot of techniques devised for getting that level. What this corollary says is that all those techniques are not going to work. Yeah.
But Grigor,
Yeah.
is this corollary to the open questions or to your theorem?
This is what I said. This is corollary to the thing I will state.
Okay.
Let me put it here so that it's not confusing. The main theorems will imply okay. So I mean, this is a corollary which I guess people care about, but the thing is, you don't go for this problem. It's if you just write it on the board, it seems intractable. The thing that you want to solve is try to understand exactly how. Just imagine what sort of things you would need in order to force MM++. Okay, but that's also too ambitious. So you say, okay, I'm not going to do MM++. I will just concentrate on some consequences, right? Like take test problems. So the test problems we had, the following are the test problems. And you can, of course, enlarge these. So first is, of course, failure of square. Just what I have here, right? So these are consequences of MM. So it will be for every kappa greater than or equal to omega 1, not square kappa. Then 2, for example, WRP. This is formal Magidor Sharap. Which is stationary reflection, right? You're saying that if you have a stationary subset of, for every kappa, you have a stationary subset of p omega 1 kappa, so countable subsets of kappa, then it reflects to a set of size omega 1. You can find a set of size omega 1 such that the set restricted to p omega 1 of that set is stationary. The SRP, which is Todorcevich, this is also Todorcevich, by the way. Todorcevich. So there is SRP, which is a stronger version of WRP. This one would say that not only it reflects, but there is a club through this set of size omega 1. Or you can write MRP. Which is a different variant of SRP. There is p-ideal dichotomy. As far as I know, I think Andreas Leeds proved that they're not equivalent. I mean, yeah, they're independent of each other. Yeah, Todorcevich again. There is the ideal dichotomy. And you can list all kinds of other things. So at the moment, it seems that all of these, this one is okay. And these are probably okay. By okay, I mean we can force over determinants. It's interesting because this begs the question, maybe this is just enough, right? For example, you can ask, is MM++ equivalent to SRP plus MRP plus PID? Okay, maybe that's it star. I don't know what else. This is also holding, right? In forcing extensions, if we do Pmax extension, star will hold. So I don't know. Maybe this is true. Another thing that I would like to pay attention to is this. I think in previous versions of these talks, I was not very clear about this. The question: can MM++ be forced over models of supremacy? It's a strange question, right? We are not. If you talk to forcing people, they immediately start thinking of iterations. We don't want to do iterations. That's not what the question is asking. We want to get theta. We want to attack this problem. So we want our theta to be omega-3. If you start adding reals, then the universe, then you have no control of what happens to theta, right? So we want the forcing to be omega closed. So this is another thing I should say. Or remark. We want to force MM++ via a countably closed. That we don't have reals.
Sorry, Grigor, did you say that in your model you have all these principles, or you just asked?
Oh, I said it's probably okay. Probably okay. Meaning there's some, there is the technique that is probably going to work, but it's there's some ideas how to do it. This one is definitely okay. I will state in a moment. These ones I don't know, but the question is, I mean, okay, SRP is nice. The other ones, it seems. When I talk to experts, they always tell me, all you need to do is do SRP, and then all consequences of MM++ are coming. I don't have that intuition, so I don't exactly know if there is anything left, right? So in some sense, checking if they really are okay or not is not very motivating, because you want to know if there is something left. So it's kind of difficult to sit and check all the details when this question is open. Maybe there is something left, right? And so I think this is what we are doing now. We're trying to see if there's anything left. My guess is that if you have a principle that's going to have a lot of concepts, maybe there is some weird forcing which we cannot do, right? But if it's going to be some kind of nice principle like these ones, then we probably will force. For example, I mean, this is more general, right? So I could put 6 here. PFA omega-1 infinity distributive 7 MM++ omega-1 infinity distributive. But these ones, there are arguments for them. I don't know if every detail of that argument will work out, but they seem to be okay. So the question is there anything left out of this? And I'm sure you'll have examples. But for a long time, I thought PID is an example, that PID is not going to be forcible. But then turned out that Todorcevic's first proof of PID dichotomy was actually omega-1 infinity distributive forcing. So it fits into the framework.
Sorry, can I just ask? MA, just normal Martin's axiom. I know it's not very exciting, but normal Martin's axiom you're getting from star already, or?
MA will hold because of MM plus C, right? We have-
Right, yeah, okay.
Because we are doing Pmax at the beginning, so we have MM plus C, we have MA. Right.
Sorry, Grigor, can I come back to the same question of Boban because I didn't get your answer? So you're saying that most likely in your model, at least 2, 3, and 4 are going to be fine?
Well, I cannot be confident. I think yes, I think there are arguments that these things should all work out. And it depends on some technical, I will state this later on, it depends on some technical fact.
Okay.
This Martin Club conjecture, if you remember from Lumini. And I think if that goes through, then all of this go through, yeah.
Okay.
But
So
again,
you
it's,
have a model, and for the moment you can check in this model that the square fails, but you expect that this model is actually satisfying much more of MM than what you're able to see at the moment.
yes, and yeah. So I guess the question is whether something is left out. If I knew that it's the same, then we would just sit down and check the proofs. But it seems like, anyway, this is just.
And this model is built on the assumption of Woodin, inaccessible limit of Woodin.
Woodin cardinal, which is a limit of Woodin cardinals. I will get to it just in a moment, okay?
Okay.
Okay, so this is the picture. The other thing that I should probably make it clear is the other remark is that we cannot force even failure of square omega 3 or even this. But let's just write 2 just to be sure. We cannot force these over models of the form again, when I say force, I always have the theta equals omega 3 situation in my mind. Yeah. So the Pmax followed by some Q is omega 3 closed. The reason is because the theory implies power set of R sharp exists, and but so then power PR sharp should have existed already in V, right? So the point is, the other remark is that we need models that have non-trivial structure of data. Meaning that it can't just be power set of R. Okay, so this is all we need. Okay, so what is going to be the source of such models? That's what I will. So I need to do some definitions. Sorry about that, but so we already seen data. This is a Solovay cardinal. So let's say delta is a Solovay cardinal. If for every beta less than delta, there is no surjection f from the power set of beta to delta with f or not definable. Right, so you cannot have OD projection from power set of beta onto delta. You can also call it OD inaccessible. It's called Solovay cardinal because these are exactly the things that are on the Solovay sequence. We need Suslin cardinal. So this is, we say A is kappa Suslin. If there is a tree on omega cross kappa, that means finite sequences crossed on the initial segments, such that A is equal to a projection of T. So we're projecting on the real coordinate, right? And then we say kappa is Suslin. If there is a set A, if you have a set A such that A is kappa Suslin, but not lambda Suslin for every lambda less than kappa. So there's some set A which becomes kappa Suslin, but it's not, but this fact, this Suslinness cannot be witnessed below. If you like sort of in general terms, why these things are interesting, if the models of determinacy can be stratified into something that is very much like a mouse. Or you can think of, if you're familiar with the Wedge degrees, you can think of just the stratification into Wedge hierarchy. Right? So wedge reducible, that means A is wedge reducible to B if and there's a continuous function such that B's pre-image under that function is A. So that's under a determinacy, that's a well-bounded relation. It stratifies power set of R into a hierarchy. Okay, so then you can start analyzing exactly when new information appears, new sigma 1 facts appear in this hierarchy. And Suslin cardinals are exactly the places where the sigma 1 new sigma 1 statements become true. And so what is the new sigma 1 statement? Exactly the fact that there is a tree. Yeah, so that's exactly the new sigma 1 statement that becomes true. And then they turn out to be very important sort of markers in the hierarchy. Okay, so this is a Suslin cardinal, and then there is the LSA cardinal. So delta is an LSA cardinal. LSA stands for largest Suslin. So this means, what does that mean? Delta is an LSA cardinal. If delta is a Solovay cardinal, so that means it's OD inaccessible, right? That meant if you take something smaller, there is no surjection onto it from any object living below. So think of the wedge hierarchy exactly. That's probably the best way of thinking. Wedge hierarchy kind of stratifies the determinacy hierarchy into V hierarchy, the way we think of the cumulative hierarchy, right? So that means if this means that if the Solovay cardinal means that if some object appeared in that hierarchy before delta, then there is no way of subjecting it onto delta. So it's a Solovay cardinal plus the largest Suslin cardinal. Suslin cardinal kappa less than or equal to delta. Plus there is a largest, I should say, plus there is a largest Suslin cardinal. No. Delta is a Solovay cardinal, and if delta is not a limit, sorry, delta is not a limit of Solovay cardinals, right? So it's not a limit of inaccessible cardinals plus the largest Solovay cardinal less than delta is a Suslin cardinal. Okay, that probably is difficult to explain.
I mean, you maybe need to say that there is a largest, the largest Solovay cardinal is Suslin. Sorry, I see. It's correct.
Sorry. The largest Suslin cardinal is this largest Suslin cardinal less than delta. The largest Solovay cardinal less than delta is the largest Suslin cardinal. Is the largest. Thank you. Is the largest Suslin cardinal. So this is probably too abstract for people who are not familiar with it, but basically in the ordinary, this is kind of an anomaly. In fact, for a long time, we were not able to understand what exactly happens here. Because in the ordinary case, when you take the two consecutive Solovay cardinals, the largest Suslin cardinal is always in between. And this axiom shows up in Hugh's book, in the big book, and he says that I cannot prove that this is inconsistent, and turns out to be actually consistent. Okay, so what is a Nairian cardinal? So we have Solovay cardinals, which are just inaccessible, but with respect to ordinal definable functions. We have Suslin cardinals. These are the places where new information shows up in the form of a tree. We have the LSA cardinals, which are this anomaly. And then we have Nairian cardinals. Okay, so if delta is an LSA cardinal, and delta out to delta is a full Nairian cardinal, I should say. Is a full. Omega, just to be precise here, I have to actually say the union of alt up to beta less than delta to the omega things here. And well, that part is not important. Yes, this concept also shows up in Wooden's book. So at some point in the book, he says, I have these three axioms, ADR plus theta regular, the LSA, and this one. He doesn't call it Nairian cardinal in the book, and says, I don't know if they are consistent. I think we still don't really know if the full Nairian cardinal is consistent, but you can define Nairian cardinals in general. So Ada is a Nairian cardinal, not necessarily full. Fullness means this part is what makes it full. Right? The Nairian cardinal, you just have only this portion. Okay, so the LSA cardinals were anomaly. Full Nairian cardinals are even more confusing. Okay, so then recently there was a theorem, and as you know, John Steele wrote that book for which he got the Carl Prize. After that book, many theorems were proven, and in particular, we understood how the Nairian cardinals can show up, the full Nairian cardinals. So this is a theorem of Steele and Wooden. So assume HPC plus delta is an LSA cardinal. There is a limit of wooden cardinals in hut. Right? So that means hut thinks delta is a limit of wooden cardinal. Okay. So then delta is a Nairian cardinal. Is a full Nairian cardinal. Still showed, assuming HPC, which is the hypothesis he defined in his book, comparison or comparing iteration strategy, normalizing and comparing iteration strategies, that book. Let's just basically HPC is saying that hard analysis can be carried out. So HPC is this is saying basically saying it's called hard pair capturing, but basically saying hard analysis works out, whatever that means. And so assuming that John proved the calculated the certain ordinals, the length of certain prior orderings, and then wouldn't use that calculation to actually show that the model is a model of CF. Okay, it's not particularly important how you do that, but let's see. I wanted to say something. Right, I said that we don't really know that Nairian cardinals are consistent. We still don't know that this is consistent. This hypothesis is consistent, but the meaning which hypothesis? That delta is an LSA cardinal that is a limit of wooden cardinals in hut. Yeah, that's, we don't know if such a thing can happen, but this theorem tells us that something is going on, right? So this was a very important theorem. And the other thing is, you see, when you have a model of ZF, then the theta of this model has to be smaller than this delta, right? Remember, delta is just an LSA cardinal, so there is a surjection of reals onto delta out in V. But when you look at this chunk type model, this model, then the theta of that model must be strictly smaller because it's a model of ZF. So
Question.
I'm sorry?
Question. Yeah, am I going ahead of myself, or is it? Are these Nairian models? Are they models of some sort of determinacy?
Yes, because they're defined inside the models of determinacy, right? See, I'm putting all countable sequences. That means all the reals are there, and this is defined inside determinacy models. So of course it will be a model of determinacy. Let me put that remark. Yeah.
Model of AD.
Will be a model of, in fact, ADR.
ADR.
Yeah, it's a good question. So let me, if you have such questions, ask me, because I don't really know what questions people have. Yeah, it's a very important question, right? So first of all, definition, Nairian model of data. That let's say gamma is L gamma union union beta less than gamma hard up to beta to the omega. Defined inside. I mean, the base theory is 80 plus, right? In fact, I like to work in this theory. Okay, so
Grigor, can you also clarify what the theta of the Nairian model is? I guess in the full case, at least in the full case, is it the largest Suslin of the LSA
Yeah,
model?
so
Okay.
remark N gamma is a model of ADR. The reason being, well, ADR is a little bit involved, but AD is easy because N gamma has all the reals. So any game you play that was determined in the parent model, and the winning strategy is on, if your game is on integers, then the winning strategy is a real. So it belongs to the Nairian model. AD is easy. ADR is a little bit more tricky, but it's not much tricky. And two, I guess, theta of N gamma is always the largest Suslin cardinal. So theta means this is the ordinal that was supremum of the ordinals that are surjective image of the reals.
What do you mean by the largest Suslin in the non-full case?
In the V, right? In V. It's the largest Suslin cardinal less than gamma.
Okay, thanks.
The other remark is that this is, if you just do the ordinary definition of L gamma union this, right, in the ordinary L construction, you're supposed to put the set at the bottom and then build L on top. So if you do it like that, you will have the ordinal height of this structure will be gamma plus gamma. But that's not what we want to do. We want to make the ordinal height be exactly gamma, right? Maybe I put that remark here too. And the ordinals is gamma. You just have to do it slowly, not just put the whole thing at the bottom. But anyway, you can do it. Okay, so what happens? Let me just take the theorem already. This is with so suppose assume HBC plus delta is an Nairian cardinal, not full, right? Delta is a cardinal. So not a full Nairian cardinal. That we don't know if is even consistent. Let now psi be the least inaccessible limit of less than delta strong cardinals of phi. Then
Sorry, Grigor, I'm a bit confused. What happens in the case that N gamma is not full? What is theta in that case?
if it's not full, then you mean, but it's a Nairian cardinal. If it's an Nairian cardinal, it's always the largest Suslin cardinal less than gamma. Nairian cardinal means this is a model of ZF, and gamma is a model of ZF. Yeah.
Okay, but what
just
is
do
the
it with
difference? The point is largest Suslin axiom. I'm a bit lost. Apologies, but I don't see what happens. So largest Suslin axiom, wasn't that the assertion of that you have a largest Suslin cardinal, and is
Means so here I mean it's called the largest Suslin. Delta is here. The largest Suslin is here somewhere. This is the largest Suslin.
Okay, so what you are losing from going from full Nairian to Nairian, I don't see exactly.
Full Nairian happens here at delta. And Nairian happens somewhere earlier, like here somewhere. So let me finish this and then I will draw a picture. Yeah. Psi is the least inaccessible limit of less than the strong cardinals of phi, then psi is an Nairian cardinal. So this means that n psi is a model of ZF. And if P is P max, and then you have to iterate, I guess, let me just do it. Add one, that to every regular cardinal. Well, let's just write Q. Q is, let's say, reverse Easton, though that's misleading to me because there are no inaccessibles. Is a reverse Easton class, right? Class iteration of add one lambda for lambda greater than omega 3. Let G be generic. Yeah. VG satisfies have M plus plus C, and it will have what did we cover? And we'll also have the for every this one you should say ego. And then now the other theorem is that the hypo is weaker than or maybe I should write that so that it's not confusing.
Sorry, Grigor, quickly. In the first theorem, do you know about square kappa lambda? I mean, you know these weaker square principles?
Just so we think SRP is holding there. So yes, I guess they all.
Okay, but you don't have like a direct, the proof itself that you have for the square originally doesn't give you
This
that.
proof doesn't work, no.
Okay.
The omega version does. Square kappa omega, that version does, but if you put omega 1, that version doesn't work. This proof does not work.
Okay.
Okay, so Mateos, so the theorem is saying that if you have a Nairian cardinal, you look at this psi, and there is also a Nairian cardinal. In fact, it's the smallest Nairian cardinal in that LSA window. And then you iterate, so you do Pmax, and then you keep adding coin subsets to all the regular cardinals. Now you don't have any inaccessible cardinal in this model. So reverse Easton is just at the end you take, right? When you do class forcing, at the end you take, the reverse Easton portion comes at the end. All the other ones are full support. You need full support because otherwise the forcing will not be closed. Right? Okay, so.
Sorry, you also get choice in this model, I guess.
Oh yeah. When I write MM, I mean choice, right? So that's absolutely, yeah, that's the whole point.
And so you expect that in this model you will get a strong reflection principle, for example.
Yeah, the point. So let me write down. Should I answer your first question about Nairian, the smaller Nairian kernels, or this question that you just asked?
As you want.
Okay. So about SRP. So there is a theorem of Solovay from, I don't know, ages ago. ADR implies omega 1 is R super compact, X super compact for all X of size R. So in fact, P omega 1 R super compact, right? So for example, this implies there is a super compactness measure on P omega 1 alpha to the omega for every alpha less than theta. In fact, he also proved, so let's call this A, D, there's a the Club filter on the omega 1 R is a super compactness attribute. This means normal fine, yeah. So the omega 1 super compactness measure on P omega 1 X is unique. Maybe I'm missing DC here, so can I just add DC just to be? But I mean, there's a nice characterization. It's in fact, it is the algebra generated by well, I don't know what the uniform terminology is, but you can call quasi-clubs. So what's a quasi-club? We have A, the omega 1 X. So A is a quasi-club if player 2 or 1 is a winning strategy in the following game, yeah. So 1 and 2, they play A0, B0, A1, B1, and etc. So conditions are AI and BI belong to P omega 1 X. They increase. And maybe just AI, and so 1 means if only if the union is in A. Okay, so you cannot convert this into club. It's a tree, yeah? Tree such that all the branches belong to A, but you cannot convert this on without choice into a club. And so this so okay, so what do we want to know? So there are the super compactness measures. They are unique, right? If they are unique, they are ordinal definable because it's the unique. Okay, and they are have this particular definition. So they're quasi-clubs, right? Now the conjecture is, well, let me just put a remark first. Suppose psi is a Nairian cardinal. Then for every alpha less than psi, right? Mu alpha intersection and psi is in psi. Well, mu alpha is the unique. Omega 1 super compactness measure on the omega 1 alpha to the omega. If the reason being, I mean, this uses some determinacy, but the point is this. So I have, remember, n psi is L psi odd up to right. So I have HUD in this model. This model is closed under OD definability. So the subsets of alpha to the omega, right, that are in the measure. Is this clear?
Yes.
Yeah. So because you have HUD already, the model nxi is closed under ordinal definability. So we have nxi things omega 1 is X super compact for every X. Okay, but we don't know if it's the quasi-clubs. So the conjecture is that nxi actually thinks that for every X, the filter generated by is an autototal.
But why it cannot reflect this second statement and psi while it can the first?
Because the quasi-clubs are not ordinal definable. So the first one is just the set of subsets of, basically the first one is because if I look at a subset of p omega 1 alpha to the omega such that A is in mu alpha, right? This is in nxi. Sorry. This is in nxi. So I can define the outer filter, but right, I just know this is a set, but I don't know why it's in the measure. The reason for it.
Sorry, this set is in HUD or is...
No, it cannot be in HUD, but it's ordinal definable because mu alpha is unique, right?
Yes.
Mu alpha is ordinal definable, and so this set is ordinal definable because
yes.
nxi is ordinal definable, and nxi is closed under ordinal definability. So if you have an ordinal definable subset of nxi, it belongs to nxi.
But why is it closed under ordinal definability? Because it.
Yeah, that's a good question that I can. It's that's because of AD plus theory. That's a theorem, I guess. A non-trivial theorem. Nxi is closed under ordinal definability. I mean, I could try to explain if you want, but it will take a while. So this
but
means,
if you have this set is in nxi, then
I'm sorry. Let me just write what this means and then talk about it. For every z in nxi, and for every a subset of nxi with a ODZ, right? A is in nxi. Yes.
Okay.
But now you cannot prove. I mean, at least it's not obvious that the quasi-clubs, right? You have a set which has measure 1. You know there is a quasi-club contained in it. You cannot prove it's ordinal definable. So what this conjecture is saying is that it's ordinal definable from something in xi. To give you some evidence, you can prove at the moment we can prove that it's true for OD. If A is a subset of p omega 1 alpha to the omega, A is in nxi, and A is OD, then nxi thinks A or A complement contains a quasi. And so basically what we need.
So the super compact measure is ordinal definable without parameters because it's unique.
Yes.
And now you say if I take an element which is ordinal definable, then I know that it contains a quasi-club.
Yes. And we need to generalize this to for ordinal definable from a countable set, which requires to do hard analysis and things like that. So it will take a while. So if we know this conjecture, right? So this is the theorem with blue, I guess. If quasi-club conjecture is true, then NG satisfies SRP. But as an evidence for these, you can also prove that NG satisfies SRP star. So the star version of SRP is basically SRP outside of an ideal.
Outside?
There is an ideal on P omega 1 alpha, such that outside the ideal, any set which is I positive.
Okay, so there is a normal ideal on P omega 1 alpha.
Yeah. And what will be the ideal? It's exactly, you take the supercompactness measure and you look at its
trace in the generic extension. I mean, at the stuff it generates in the generic extension.
Right. Yes. And this already shows up in Wooding's work. If you look at, I mean, you have remark. Wooding showed that LR mu, so this was, oh, sorry, LR mu G and mu is the couple on P omega 1 of R. So you take the club filter, you construct from it. We have exactly the same issue. It's no longer the club filter inside the model. Because it's not the club filter, he's only able to show that the star version holds. If it was the club filter, then its dual is the non-stationary ideal, so you're good. Right?
So can I so the picture would be that this generic extension of the Nairian model satisfies, let's say, MM++, which in the ZFC standard version would be a universe where there are no large cardinals. Yes. MM++ plus there are no large cardinals.
Yes. Yes. Yeah. That would be sort of the end where this is going. Yes. Oh yeah, and then we ask about the so full Nairian versus Nairian. And so there is this theta sequence. This is the enumeration of Solovay cardinals. Okay, so one important fact about them is Wooding's theorem. So hard things theta alpha plus 1 is Wooden. Right? So we are in the model of determinacy. So this is 80 plus theorem. Okay, now
Grigor,
yeah.
do you want to give a pause for 5 minutes? Or
Can I finish this and then we do it?
yeah.
Okay, so now we have what? We have the full Nairian cardinals are exactly these theta alphas, right? Is some theta alpha plus 1. Just the Nairian cardinals appear. Nairian cardinals appear between so you have so if eta is a Nairian cardinal, then there exists some, and there is alpha such that you have theta alpha plus 1. This is not necessarily a full Nairian cardinal, right? So I'm not saying theta alpha plus 1 is a full Nairian cardinal, but eta will sit somewhere here. Yeah, this is it. Such that theta alpha is less than eta.
And theta alpha would be its theta in the Nairian model.
Yes, and theta alpha is theta of the Nairian model.
Mm-hmm.
This is exactly what happens.
And,
And the psi, the other remark is that the psi of the theorem is the least Nairian cardinal.
so the psi is the least, which is the assumption was that this psi was
Yeah. So we started with any Nairian cardinal,
mm-hmm.
and we take the least inaccessible limit of less than delta strong cardinals of phi. You could define that as just the least one that will be model of ZF, that will satisfy model.
Okay.
It's equivalent to saying psi is the least Nairian cardinal.
Okay.
In that interval, in this,
Mm-hmm.
so you take delta. I guess in the picture here I put eta,
Mm-hmm.
but it will be the least one in that window. Yeah. So Rahman, you want to take a break? Rahman? Oh, he took a break. So should we take a break or should we?
Yeah, maybe 5 minutes.
Okay. All right. Are we recording the break or are you pausing it?
I pause it.
Okay. So let me say it again. We don't know how to force choice of a full Nairian model. Don't know if there is an inner model in the forcing extension that has omega-2 approximation and covering property, and like in non-trivial model. V, of course, has it, right? Yeah, we don't know. If NG can have an accessible cardinal. Well, I mean, Woodin conjectured that you cannot have Woodin cardinal, but let me, just because we are just speculating, let's just conjecture that if this is a speculative conjecture, right? It's not like I strongly believe that this is true, but I expect that something like this might be true. If delta is a full Nairian model, a full Nairian cardinal, and kappa less than delta is Woodin inherent, and less than delta strong, then and delta thinks kappa is Woodin. Okay, well, let's not speculate anymore. So this is just to give you an example of how large cardinals could end up in that universe, because Woodin now conjectures that you will not have large cardinals in NG. So In fact, you can let's just put this as opposed to so this versus conjecture of Wooden, which he stated in the exotic models paper. plus class of Woodens implies negation of star plus. What this conjecture is really saying is that you cannot have a forcing extension of a Nairian model with Wooden cardinals. This is what the conjecture is. Of course, I don't understand. I mean, this means that the Wooden cardinals are allowing you to, yeah, people who know SSP forcings, right? So what sort of SSP forcings can you cook up from a Wooden cardinal? That's the kind of thing that's going on here, right?
Can I say something? So
yeah, of course.
if this is true, there should be some combinatorial consequence of MM++ together with the Wooden cardinal, or class many Woodens that doesn't follow just from MM++.
Mm-hmm. Right.
But the existence of Matthew's result, the existence of a Lever function on omega-2 isn't an example. But okay, I don't know if it implies this negation.
Right. So you have to think, maybe we should study Matthew's paper. Matteo, you're next.
I have no idea if it can have any relation with the non-star plus.
Well, but I mean, you have to start thinking what sort of SSP forcings exist in the presence of Wooden cardinals, right?
Right. So
But this is what I mean. But Boban said if there is something from MM+++ class of Woodens, which does not follow from MM++.
Well, the NS is saturated is a forcing that you need Woodens to make true.
but you already have MM++, so you do
Yes.
have NS saturated.
But you cannot reforce NS is saturated if you don't have Woodens.
Okay, but why would you want to reforce?
Because you want symmetry in the universe, so essentially you should be able to remake what you are making true at a certain stage. It should not be something that you cannot make true anymore.
See.
Right. Let me write some. Boban, you want to say something? Go ahead.
No, go ahead. No.
So I just want to next say a couple of structural things about the Nairian model that are used in this proof, and then we just emphasize that we don't know how to get these things for the full one. Yeah. So. Structure of and psi. So psi is the least Nairian cardinal in not, I don't mean literally the least, but in any window, right? At least limit of less than the plus strokes. Least inaccessible. Okay, so first definition, suppose x is any set, x is a set, and theta x is the supremum of alpha such that there is a function from x on f surjection, right? So the following is true. This is PLS. And psi set is in and psi. Maybe I should put it in the next page. In and psi. Like kappa minus 1 b omega. Or I equals j plus 1, sorry. Kappa I the theta of kappa j to the omega, and for limit I, then kappa I is the supremum of I j less than I kappa j. Right, so this is the theta sequence. You start with omega to the omega, then I guess this is kappa minus 1, then we get kappa 0, which we usually call theta. Right, then we get kappa 1, which is theta kappa 0 to the omega, and etc. So, so kappa I plus 1 equals kappa I plus or I greater than or equal to 0. So not for minus 1. Theta is not equal to theta, right? Sorry. I not limit. For limit ones, this is also not true. True, 2, if I is limit, kappa I plus 1 is strictly bigger than kappa I plus 3 for all I kappa I for all I bigger than 0, yeah, greater than or equal to 0 is strongly regular. I.e., if beta is less than kappa I, then any function is bounded. Kappa I kappas of course this is false for limits, right? I should be more careful about this. For all for I equals 0 or I successor, kappa I is strongly regular. 4, there is some kind of if you're familiar with fine structure, there's some kind of acceptability. If a subset of kappa 0 is constructed at some point, then it shows up, then it's constructed before kappa 1. So the power set for every I, power set of kappa I is contained in n up to kappa I plus 1, which is L kappa I plus 1, yeah, up to kappa I plus 1 to the omega. This is key. And then there is also a reflection, which is used in a proof of DC for every, right? So these kappa i's are basically the cardinals of n, except to the limit steps. And the limit steps, I mean, my prediction is that it limits, because of that, you end up inside a new determinacy model. I don't know what's going on in there, but it seems very interesting. So for let's say I0 less than I1 less than I2, right? I think lambda 0 be kappa I0. Lambda k be kappa ik. Sorry. Lambda j to be kappa ij. Right? So lambda 0 is kappa sub I0, etc. The following holds. X is in n up to lambda 2. So I take something from the highest one, some any set. Then there is beta of size lambda 1. Such that and an embedding pi from n up to beta into n up to lambda 2, right? Elementary. Such that n up to beta kappa lambda 0, sorry. Is a subset of n up to beta. You may ask, why do I need this property? So let me take the rest of the time explaining to you why. At the end of the day, the hard part is to force choice. If you look at there's a paper by 6 authors from the Square meeting in 2011 or so. By Square meeting, I mean the Square meeting at AIM. And there we had a proof that you can force failure of square at omega sub omega 2 of a model of determinacy. And if you just take that proof and implement in this context, it just goes through. So proving that square fails is not the hard part. Proving that the axiom of choice holds is the hard part. And this reflection is needed for that proof. So let me remark that this is exactly what we don't know how to do for the full Nairian model. We have no understanding of the cardinal structure of the full Nairian model. We have no idea what's going on. Another thing I should say here is kappa I plus 1 is the least less than delta strong of hard above kappa I. So it's a very coherent picture. We start the strong cardinals become the successor cardinals. We know exactly what these cardinals are. We know exactly how they behave. So we have this reflection. So we have a lot of stuff that we know about them, and that's why we can force choice. Once you go beyond that region, it's total mess. It's chaos here. And I would like to use the word chaos because people usually say, you know, things in mice are very canonical. It's completely chaos, complete chaos here. It's complete chaos. So if you think mice or determinacy models are not chaotic, please spend 1 hour in the full Nairian model and then you will run out. It's just completely unapproachable, extremely difficult, it seems at the moment. But maybe, you know, over the time we will have some understanding. Okay, so how do we prove let's see. The thing that you should keep in mind is this regularity. This one, number 3. So let me give you an example of how you force. How can we forcing? Let's say DC Aleph 2 over NG. So we want to. I mean, what do I mean? Why does NG satisfy? NG satisfies DC Aleph 2, right? So why? The thing that we have to use is Wooden's theorem that if you just do Pmax, then DC omega 2 holds for relations that are on the reals, right? Okay, so the idea is that we know, and just the Pmax portion, so the GB, G0, G1, and etc. Right, so this is for Pmax. This satisfies DC Aleph 2 for relations on R, or relations on R, on well, I mean, this is kind of true because we know well-ordered reals. So we will use reflection. So we would like to use something like 6, right? So we use something like not 6, 5. 6 is the 5. Reflect to a set of size R and use DC Aleph 2. Right, so you have some big relation, you want to prove you can make on Aleph 2 many choices, right? Okay, but the relation is giant, so you take a whole of size. Well, you would like to reflect it down to reals, but there is going to be a caveat because remember, because we forced first, you really have to reflect to something of size kappa 0, not So you really have to reflect to size kappa 0 and then pull it down to it. Anyway, because we forced first, because Pmax has size R, we need to first reflect the set of size kappa 0. What do I mean by that? So let R be some relation in N up to some lambda. Lambda is one of kappa i's, kappa successor ones, right? It's a name, sorry, it's a P, let's say it's a Pmax name. I mean, even you see the rest, if I show, I guess I should make that remark before I go on because it will confuse. It is enough to show ng0 satisfies DC Aleph 2. Because the rest of the forcing is omega 3 closed, right? So DC Aleph 2 is preserved under Aleph 3 closed posets. So it's enough to prove that just the Pmax extension already gives you DC Aleph 2. Right? And this Wooden didn't prove this, right? He only proved this for relations on that in L of power set of R, basically, not the ones that will show up above theta. Okay, so we fix now some relation. So let R be some relation on in n up to lambda. So lambda is some kappa I plus 1, right? And now we go back to our picture. This was kappa 0. I have lambda somewhere up there. And so I reflect to some point down here. And there is the previous one, right? This is kappa I plus 1. And I have kappa I. My R shows up here. So I want to reflect this down to some, it's a name, sorry. The Pmax name. Here. Well, DC Aleph 2, so that means the relation is omega 1 Aleph 1 closed, right? So for a name for a relation Aleph 1 closed or omega Aleph 2 closed, I guess. Aleph 2 closed means it's closed on the omega 1 sequences, right? So Aleph 2 closed relation in here, right? So it's a name. Okay, we can collapse it down here somewhere to n up to beta. So fix beta of size kappa 0 such that and up to lambda with a R dot is in the range of pi, and B n up to beta is closed under R. So you take the relation, you reflect it down to a place where we are closed under R sequences. We can do that by this reflection property. By this reflection property. See, I can close it under lambda 0 to the omega. Take lambda 0 to be omega itself, then n up to beta will be closed under reals. Right? So that's what we do. The point being that now I can lift pi. We can now lift pi to n up to beta 0 into n up to lambda to 0 and still and have n up to beta G0 under Aleph 1 sequences is in NG0. That's the point of requiring R closure. If you don't require R closure, you won't be able to prove that it's Aleph 1 closed in the extension. Okay. So what's the point now? The point now is that we will have lift pi to pi plus. Right? Now, to this Aleph 2. Sorry, my Alephs are terrible. For pi plus inverse R. So, okay, that must be awful. For S, the I plus P image of R. Okay, so how are we going to do that for S G0? Right, so how are we going to do that? Now we use, so here it's a little bit easier now, because my relation now is living on a set of size kappa 0, right? So here we now have S dot G0 is on a set of size kappa 0. Well, it's really size kappa 0 to the omega. So what we do, so say S dot G0 is on some set X, and pick F, right? So we now can pull S dot G0 to a relation W on kappa 0 omega. But kappa 0 is omega 3. Yeah. And all I need is omega 1 closure. So that means I can find, beta less than, I already have beta. So I can find some gamma, which is less than omega kappa 0, such that it's omega 3 in NG0, right? It was, it's the theta, so it's omega 3. Okay, so can find gamma such that the relation restricted to gamma omega is Aleph 1 closed. Sorry, not this relation. That relation is not on the W. Let's make some justice to Alephs. Okay, Aleph 2 closed. Aleph 2 closed means closed under omega 1 sequences. So all the omega 1 sequences from W have an upper bound in W. But now I have DCR omega 2 exactly for these relations. And we have DC for W less than gamma omega. So now apply the inverses of the embeddings, right? So now apply 5 plus OF inverse to the branch, to the thread. So the idea is we take our relation, collapse to a place where we already have DC, yeah, take the thread and pull it up. But we need the stronger closure property, otherwise we cannot lift the embedding. We need the reflection with the stronger closure property. Okay, so I mean, I don't think I should say anything more than this, but the key point is that this type of analysis, these 5 points, is exactly what we don't know for the full model, and it's the same old problem that inner model is. I should maybe say a few things here about consequences of inner model.
Can I ask you one question? So
Yes.
this reflection that you have is really like super compactness. Is it?
Yes, I don't exactly need to. Let's see. So this
So it is something like saying that kappa is kappa plus 1 super compact or something like this.
In the Magidor sense, but it's not exactly that because these are not V's. It's are not rank initial segments, right? So.
Okay.
But also,
So in this Nairian model, you have this version of super compactness, not just at omega 1, but higher up.
Yes, that's because of there's a theorem of Jackson. Jackson, I think. The class implies all Suslin cardinals. Are less than theta super compact via all the measures, but these are ordinal. So no longer in the solo-based case, for any set X, you have a super compactness measure. Here, these are literally on ordinals, right? If delta is Suslin and alpha is less than theta, then there is a delta super compactness measure on E delta alpha, not on any set, just on ordinals. And they go down, so we can, using this reflection, this reflection, you can prove that the Nairian model is closed under the theorem. Again, the BLS. In the parent determinacy model, and up to psi, let's see, so for every I and up to kappa I plus 1, well, and up to kappa I less than kappa 0 is subset of n. So the n is closed under less than kappa 0 sequences. Kappa 0 was the theta. So for example, it's closed under omega 2 sequences. And is closed under omega 2 sequences. So you get that from here, you get the answer as well. So that would be super compact. I don't know how interesting this is because it's not super compactness measure on all sets, just on ordinals. But there is a, I mean, you guys always tell me that omega 2 is a super compact. So here is, it is. I wanted to say something about.
Sorry, Grigor.
Yeah.
When saying all these theorems by n, you mean n and delta, where delta is Nairian cardinal, or precisely n psi?
And psi. And
So
psi.
where psi was this smallest Nairian cardinal.
Yes. So we don't even know this closure for full Nairian model. It's not known. Yeah, but I wanted to say something. Yeah. Okay. So I don't remember what I was saying. Oh yeah, the limit case. I should say for those who are interested, this case 0.2. I guess people who are interested in generalized descriptive set theory might be interested. So example, let's take kappa omega, right? So kappa omega plus computed inside n psi is actually kappa omega plus of L and up to kappa omega to the omega, which is smaller than kappa omega plus 1. And this means that this model L is a model of some higher determinacy. I don't exactly know what that means because we don't. For example, you could try to prove a specific question would be, right, is kappa omega plus measurable cardinal in that model. I think this is a key point because you see, when you keep adding, because I don't know what kappa omega plus is, right? Well, okay, I know it's this thing, but I don't know it's definitely not kappa omega plus 1. So, but I don't know anything about the cofinality of kappa omega plus. It could be a singular cardinal. So, for example, it's not known even if it's regular here, right? When you start adding these coin subsets, the successor of kappa omega, imagine you added coin subsets to all of these kappa i's, and you got to kappa omega, right? The successor of kappa omega, we don't have any idea what that is. But because we proved inductively DC, so we have DC kappa I for each I up to that point, we know it's a regular cardinal. Because if it was singular, it would not be the successor cardinal because this is DC kappa omega holds. So because it's a regular cardinal, you can add a coin subset to it. So to me, this is kind of I mean, it's kind of an ATAC solution. It would have been nicer if we actually knew what kappa omega plus is in the final extension. In the final extension, it could be kappa omega plus 1, or it could be smaller. We don't really know what it is at this point. And I think maybe there are some questions you could ask, which you could answer if you knew exactly which. For example, you could ask, you could ask a little bit stronger. So if, I guess I could just write an observation. If kappa omega plus of ng is kappa omega plus 1, then add of power set of kappa omega thinks kappa omega plus is a measurable cardinal. Right, so these are kind of questions that Alejandro and Seba were thinking about. So whether you could have successor cardinal measurable in some symmetric extension. But we need to know exactly what the successor is. It seems like a problem that's tied to this type of question. And we have no clue. At this point, we have no clue exactly what the successor of kappa omega is in the final extension. And probably we should stop here, yeah? Okay, we stop.